AQA, A-level physics, engineering. This is video number 6 in this playlist, and it's about rotational work and power. And this bit of the syllabus is what we're going to be looking at. So, work equals force times distance. So in a straight line, there's a force. This bloke is applying a force to this object. It produces a displacement S, and work done, in fact, is our definition of work. Now that work may be accelerating the object, or it may just be done against frictional forces. This box might move at a steady speed, in which case the work is done against friction, or the box might speed up, in which case it's done increasing the kinetic energy of the box. But anyway, you know this is GCSE. Now, power is force times velocity. So power is the rate of doing work. So basically the work done in a certain time, and if you divide by time on both sides of the equation, well, displacement over time is velocity. So we get power is force times velocity. Now look at this. Work is torque times angular displacement. So work is torque times theta. And again, the work might be accelerating the object, giving it kinetic energy, or it might just be work done against a frictional torque. There's nearly always a frictional torque involved, and you should be aware of that. If it says ignoring any friction, great. Otherwise, there'll be a frictional torque somewhere. And again, it's not power is force times velocity. It's power is torque times angular velocity. Have a go at this. A ceiling fan has a moment of inertia of 1.2 kilogram meters squared. When it's turned on, it rotates at 210 revs per minute. When you switch it off, it takes 7 seconds to slow down and stop. Now, assuming it is constant, calculate the frictional torque. Now, in real life, it won't be constant because most of that friction will be air resistance. And as it slows down, that will get smaller. But assuming it's constant, calculate the frictional torque, and then using that, calculate the power of the motor when the fan is operating. So have a go yourself. The answers are in 3, 2, 1. Okay, so T equals I alpha, moment of inertia times the angular deceleration. Okay, 3.77 Newton meters. Then when it's spinning round, power is torque times omega. So 3.77 times radians per second gives you 82.9 watts. And here's another one, a bit more practice. You've seen a Van der Graaf generator. Sometimes they have an electric motor. Sometimes you turn the handle to make it turn around. So a student turns the pulley of this wheel with a steady force of 20 newtons. In 30 seconds, it rotates 24 times with a constant angular velocity. Calculate the following, blah, blah, blah. Have a go yourself. And the answers are in 3, 2, 1. So the angular displacement, it's just the number of revs times 2 pi. The torque applied to the pulley is this force times the radius of the pulley. The work done by the student, well, I've done torque times angular displacement. And then the power, I've just done that divided by time. One last word, just a little word about gears. You know, like a lever is a force multiplier. Well, gears are torque multipliers. If you've got the same power in, power out, then the small gear there whizzes round fast, but the torque is small. The big gear turns around much slower, but the torque is larger. And then depending on how fast the wheels are going, you can change gears on a bike. So power in equals power out. So T omega on that side equals T omega on that side, ignoring any friction between the gears, that is.